So I'm going to be talking about additive forms and conditions in which we can say they have non-trivial zeros based solely on the number of variables. So I use the term additive form. I know many people use diagonal form. I picked this up from the original paper by Davenport and Lewis and kind of maintain the tradition of calling them that. But this is an additive form or diagonal form. These are homogeneous forms with only the variable to the power of d terms. And what we're interested in is when these forms represent zero in a non-trivial way. So obviously they represent zero when all of the variables are equal to zero. And the question is, do they represent zero in any other ways? There are certain fields, these are sometimes called Brouwer fields, in which all that you need is a sufficient number of variables to guarantee the existence of a non-trivial zero. Just as a historical note, these are named after Richard Brouwer, who was the advisor of Donald Lewis. So that makes him an academic ancestor of many of the people here today, including myself. So if this number exists, then we can define a function. This function is well defined that gives us for a particular degree, the degree of the form, and a particular field, Brouwer field, what is the minimum number of variables such that the existence of a non-trivial zero is always guaranteed. And so we call this function gamma star. So the gamma star of dk is well defined by this. And Artin conjectured that for all p-adic fields, so all fields of p-adic numbers and their extensions, their finite extensions, that this function gamma star is bounded by d squared plus 1. I'm being a little bit imprecise. Artin didn't quite conjecture this. He conjectured that this was true for all homogeneous forms, but that conjecture is false. So counterexamples are known for that. But as far as we can tell, it seems to be true for additive forms. And I believe that it is true. Okay, so on this question, specifically on the question of this d squared plus 1 bound, there's some progress. The first progress in this direction was the original paper by Davenport and Lewis, in which they established that for every field of p-adic numbers qp in any degree, that gamma star is bounded by d squared plus 1, and this bound is sharp. That is to say, there is a degree, in fact, for every qp, where this bound is an equality. Specifically, when d is equal to p minus 1, where the p is the p in qp, you have equality. By the same argument, you can give or I should say, what we mean specifically by this is that a form, an additive form, exists in p minus 1 squared p minus 1 squared variables, which does not have a non-trivial zero over qp. This same form, or an analogous form, exists for all totally ramified extensions of qp. And so we get a similar situation for all of those extensions. But as far as we know, these are the only situations where this occurs. And I believe that this conjecture is true, that this function is bounded by d squared plus 1. But I would go further and say that aside from these particular cases, there is a much lower bound. And I would even be so bold as to go a little further and say that this bound is strictly less than quadratic in D. Okay, so that's that paper from 1963. We have to go quite a bit into the future to see the next d squared plus 1 result. And that is this paper by David Leap and Luis Sordo Vieira in 2018. And that is for any unramified extension of QP where P is an odd prime, and any degree gamma star is bounded by d squared plus 1. In fact, they went a little further. I'm trying to restrict myself from talking about results that are stronger than the d squared plus 1 bound, but I'll talk about this one. That in fact, they prove the stronger result that this other function, delta of dk, is bounded by d plus 1, and this is a function that describes how many variables guarantee the existence of a non-trivial zero if all of the coefficients on those variables are not divisible by p. I might be stating that slightly imprecisely, but that's the basic idea. And with the help of the pigeonhole principle and just a tiny bit more, you get the d squared plus 1 bound from this. So this is stronger. We have, David Leap and I have recently done some work to show that this is in fact a strictly stronger result, that it in fact implies a bound that is strictly lower than d squared plus 1. So we have this for the basic fields themselves, the fields QP, all of their unramified extensions with exceptions. And more recently, in a paper by doctors Gipala Miranda, Gogino, and Knapp in 2022, we have that for any of the quadratic extensions of Q2, and there are 7 of those, 6 totally ramified and 1 unramified, and any degree D that is not a power of 2, then this bound holds. And I can add something very small to this. For 4 of those ramified extensions, and in fact, I know this is true for some of the other extensions as well, that for one particular power of 2, 4, that gamma star is exactly equal to 11, which is, of course, less than d squared plus 1. Okay, so that's pretty much all that's known on this question. And so I'm going to put forward a little bit of speculation. I think that this conjecture is true. When you look at how these results are proven, the kind of tools that are used, and you think about d squared plus 1 as a number of variables, it just seems so incredibly large that it's hard to see how the conjecture could be false. But we don't have a proof of it yet. So if someone were to pressure me into saying where I would expect to find a counterexample, I would say that it would probably be an extension of 2. The degree of the form would probably be a degree that's a power of 2, as we see in this result that I mentioned from myself and David Leap here. For degree 4, we see that 11 is, well, it's not quite 17, but it's quite a bit closer to d squared plus 1 than many of the other results for exact values that we have. And for a variety of reasons, we might expect it to be in a degree, in an extension that has a high degree of ramification. So today, for anyone that has any hope of looking for a counterexample, I want to undermine a little bit of that hope by giving a proof in a case where we have a high degree of ramification, in fact, an arbitrarily high degree of ramification, and maybe I can give some tools for dealing with that situation. Yeah, so that's what I'm going to talk about, and that's this theorem, that when we look at the degree being 2 times odd, any odd number at least 3, and K is any totally ramified extension of Q2, no matter how high a degree of extension, then gamma star of dk is bounded by d squared over 4 plus 3d plus 1, which is strictly less than d squared plus 1. And I hope to show that we can actually achieve a result like this with fairly little work. So maybe someone will be interested in picking this up and extending it. Okay, some preliminary establishing common language so that we can communicate about this. The degree that we're talking about, D, is equal to 2m. And so m is going to represent this odd factor. K is any totally ramified extension of Q2, as we said. We'll call its ring of integers O. We'll pick a uniformizer of this ring of integers, which we'll call pi. The degree of ramification will be, we'll call it E. That is to say that 2 is represented in this, using this uniformizer as pi to the power of E times some unit. And we can assume without loss of generality that all of the coefficients belong to this ring of integers and are non-zero. Okay, going further, any non-zero alpha in this ring can be written in a unique way, which I'll call its canonical representation as pi to the L times some power series in pi, where the coefficients in this power series are either 0 or 1, and this leading or this lowest order coefficient is 1. It's non-zero. That's what I mean when I say that this is a unit. This lowest order coefficient is non-zero. So I'm going to refer to this L as the level, and more usefully, I'm going to, anytime we have a variable that has a coefficient that is in level L or has level L, we're going to describe that variable as being in level L. And so you can think of this as a sequence of bins, one for each of the possible levels, and the variables are going to be residing inside these bins. Okay. Now, by this change of variables where we pull off some power of pi and move it into the dth power with the variable, and then replace that variable with a new one, then we can think intuitively as a variable being moved up or down some multiple of d levels. And another way to think of this is that we'll just consider the levels modulo d. So we can really think of these forms as only having variables in levels 0 up to d minus 1. Now, thinking of it this way, multiplying all the terms by pi moves every variable up one level. We now may have things in level d that were previously in level d minus 1. By this change of variables, we can move them down to level 0. And in this way, we can think of sort of rotating the levels around in the form. And we can do this a certain number of times and maybe get the form into a more convenient, into a more convenient form, into a more convenient configuration, let's say. And one specific, very convenient configuration of variables, we've referred to this, putting it into this form, as the process of normalization. That if we let this describe the number of variables in level 0, then that number of variables will be at least the total number of variables divided by the total number of levels, which is d in this way of thinking about it. And the number of variables in the first 2 levels will be 2 times that amount, at least 2 times that amount. The number of variables in the first 3 levels will be at least 3 times that amount, and so on. In fact, we'll only use the first 2 for this result, but this will be very useful at the end. Okay, now this is the big tool that's used in most of the results that I talked about. I think actually in all of the results that we talked about. So consider a collection of terms in our form, and then think about all of the values that can be represented by that collection of terms. So if we make some substitution for the variables, we can represent some value, and we can take that representation and turn it into a coefficient on a brand new variable by simply making the, assignment where we take the original assignment and multiply each of those values by this variable. So I think this is clear. We can make this substitution instead, and all of the terms that we were looking at are replaced by this new term, b times y to the d, where B is any value that could have been represented by this collection of terms. So we can think of this as taking these terms and kind of squashing them down into a new one, getting a new variable. And because of this, this process is referred to as contraction. Now, one thing to note, one simple observation to make, is that when we perform this contraction, the level that this new variable will be in will be at least as high as the lowest level of any variable that was used in the contraction, right? So that's pretty clear. Another thing to note in our specific situation that we're looking at right now is that if we take any two variables in the same level, if I could just back up one slide, they're going to share the same L here in this representation. Excuse me. And their alpha 0 term, their lowest order term in both cases will be 1. And that means that we can add those two values together to get a new value that is has a 2 right here in this lowest order term. Now remember that 2 is represented by pi to the e times some unit, which means that term gets moved up. E terms, it gets moved up to some term up here, some term further down, depending on what e is. And so this will now be 0, and a higher power of pi can be divided out of this. And so it's at this new variables at a higher level. So if we contract any two variables on the same level, we will go up at least one level. Now we need more than this. We need to know more about this, more about the contractions than this. And so I'm going to talk a little bit. Well, before I talk about that, let me introduce Hensel's lemma. Okay, so the idea with these contractions is that we contract a collection of variables and we get a new one at a higher level. And if we can continue doing this process enough times that we get a variable at a sufficiently high level, then Hensel's lemma tells us that we can deduce from this the existence of a non-trivial 0. And so specifically for our situation, I've just boiled it down to the bare essentials. If we can perform a contraction or a series of contractions with a variable starting at some level, let's say k, and produce a new variable at some level k plus 2e plus 1, then the form has a non-trivial 0. And I've stated this kind of pithily down here, that if we can go up 2 plus e levels, we win. Thinking of this kind of like a game. If we can perform contractions that allow us to go up 2e plus 1 levels, then we're done. We have the existence of a non-trivial 0. Okay. Now coming back to the kinds of contractions that we can perform, these are dependent on what the Deith powers are. And so I'll establish a little bit of facts about those. So if we pick any k that's greater than 0 and we look at 1 plus pi to the k to the power of d, then we can pull the factor of 2 from the d inside. And we, of course, get this term that's divisible by 2. And this gets rewritten, or it is divisible by a higher power of pi. So this is divisible by, exactly divisible by pi times, or pi to the power of k plus e. And then it's multiplied by some unit that's established by our choice of uniformizer. Okay, now if k is less than e, then clearly this last term, this pi to the 2k, is a lower order term. It has a lower power of pi in it than every other term that we would get from this u times pi to the k plus e. Sorry, u to the power of k plus e. And this means that if we look at the Deith power 1 plus pi to the k to the d, then we get 1 plus pi to the 2k in these cases for these values of k, and then some higher order terms. But there are no intervening lower order terms between the 1 and the pi to the 2k. So we're going to use this to allow us to get some information about these contractions in this way. I've put the arithmetic here so that you can see that I'm telling you the truth, but the essential idea is that if we have a contraction that goes up 2k levels, so let's say we start from level L and we go up 2K levels, so we get this value being represented by our terms right here, so this C. Then we can replace a substitution, beta I of xi with beta I times 1 plus pi to the k, and the consequence of that is that we'll have an extra pi to the L plus 2K term. So we get an extra thing there in that level. We get an extra 1. And when we add those two things together, that becomes a 2. That 2 gets shipped off to a higher order term. And that means that the result of this contraction, instead of going to level 2K or going up 2K levels, goes up some amount of levels more than 2K. And we can't say exactly how many. And the complement of this, let's say, is that if the contraction were to go past level 2K or go up more than 2K levels, then we can do the same thing, get an extra pi to the L plus 2K term, and then that contraction will now go exactly 2K levels. Now, these facts allow us to have some control over the contractions and where the resulting variable ends up, and this turns out to be very important. So I've written this kind of a distillation of what I just said, and I'm not very good at formatting things in LaTeX, so it kind of looks a little bit like a poem. But if a contraction will go up to go up 2K levels, we can make it go up at least 1 more than 2K levels, and if it goes up past 2K levels, we can make it stop at 2K for any k that's less than e. For example, let's suppose that our degree of ramification is greater than 2, and we have a pair of variables in level 0 that contracts to level 4. Well, that's the k in that case would be 2, which is less than e, and so we can instead arrange this contraction to go to some unknown level that's greater than 4. Okay, so the consequence of this is that whenever we perform a contraction, we can choose, let's say that our contraction starts in level 0, we can choose for that contraction to not go to levels 2, 4, 6, and so on, all the way up to 2e minus 2. Right, so all of those k's will be less than e, from 1 all the way up to e minus 1. So we can skip all of these levels, or we can force our contraction to stop at one of these levels if it would have otherwise gone past them. Okay, so all of those tools are things that already existed in the previous literature, in the previous results. You've seen these things before, probably, if you're familiar with this. I'm going to introduce one very small addition. This is a combinatorial lemma, which will be useful, but not so difficult to establish. Imagine that we have a bunch of objects, and for any pair of these objects, it gets assigned to some bin, some unordered pair. It gets assigned to some bin. How many bins are, sorry, if you know the number of bins, how many objects do you need in order to guarantee that 2 pairs get assigned to the same bin? It turns out that you just need the number of bins plus 3 objects. Maybe this is a surprising result. Okay, so this is fairly easy to establish. We suppose the contrary, and in that case, every bin will contain either 3 pairs of the form AB, AC, BC, at least at most those 3 pairs, or all the pairs will have one of the objects in common, let's say AB, AC, AD, AE, and so on. In the latter case, the bin contains at most m plus 2 pairs. You can see that obviously. Suppose there are k such bins, and if all of these k bins contain that many pairs, all m plus 2 possible pairs, then for any 2 of these bins, some pair is shared between both of those bins. Right? There's a bin that has object A in common and a bin that has object B in common. So there's AB will appear in both of these bins. So we're going to remove one pair from each of these pairs of bins, and that gives us k times m plus 2 minus k choose 2, or k times k minus 1 over 2 pairs in those K bins, and in the remaining M minus K bins contain 3 pairs. So we add this up, we do a little arithmetic, and we see that this is strictly less than M plus 3 choose 2, which is the number of pairs that we have. And so clearly we have a contradiction. So that establishes the combinatorial lemma. Okay, so now let's begin proving this this theorem with the tools that we have. I'm going to give you a couple of lemmas. Suppose that we have a level K that contains at least M plus 3 variables. Then some number of these variables, at most 4, can be contracted up 2e levels. So we'll go from level K to level K plus 2e. So without loss of generality, let's assume K is equal to 0, and we're going to be doing that in all the lemmas. So let's just say it once and for all now. Contracting any pair of variables from level 0 results in a pair that's free. Sorry, I didn't introduce that terminology. Excuse me. It's free in levels 2, 4, all the way up to 2e. So what I mean by free, I meant to say this earlier, is that we can either make the contraction bypass these levels or stop in these levels. So we're going to say that because it's free, we can choose our contraction so that we can skip levels 2, 4, all the way up to 2e minus 2. We can assume that this pair contracts either to an odd numbered level or to level 2e. If it goes up to 2e, we're done. That's what we wanted to establish. So we assume that it goes to an odd numbered bin, an odd numbered level. I'm getting ahead of myself. There are at most m such levels because we're looking at degree 2m. And so because we have at least m plus 3 variables, we have 2 of these pairs that contract to the same odd level bin. Now we can perform another contraction in this odd level bin, and the free variables are the ones that are at an even offset from that one. So if we contract it to level j, that will be free in levels j plus 2, j plus 4, all the way up to 2e minus 1. And also free in j plus 1, j plus 3, all the way up to 2e minus 2, like before. And so the resulting variable can be contracted straight all the way up to level 2e, and we're done. Okay, this next one is a little more complicated to state, as you can see, but it's fairly simple to explain, and I'm going to do it visually. So let's imagine we have a pair of variables in level 0 and a pair of variables in some odd numbered level, and this pair contracts past this pair. Okay, so 2 things can happen. So first of all, because this is in level 0, we can assume that it contracts to an odd numbered level. So let's say this is some odd numbered level here. Now this pair of variables contracts to some even numbered level because it's free in all of the odd levels, and it will either contract to somewhere before this one or somewhere after this one. If it contracts to after this one, then because it was free in this odd level right here, we can make it contract right here. And then we can perform another contraction, and just by the same reasoning as in the last lemma, that contraction can be made to go all the way to level 2e. If the contraction goes to this even numbered level before this odd level, then remember that this contraction or this variable was free in that even numbered level, and so it could be made to go there instead. And again, we have the same reasoning, and we can go to level 2e. So that's what's going on in this lemma, but it's a little more difficult to state precisely. And the proof is a little more difficult to state as well, but I think you get the idea. Okay, now we're going to put those 2 lemmas together in 4 different ways, and that's going to give us our result. So suppose a level contains at least m plus 7 variables, then the form has a non-trivial 0. So we can assume the level containing, well, let's assume it's level 0. We have at most 4 variables in level 0 will be used to produce a variable in level 2e by the first of our 2 lemmas. That leaves us at least m plus 3 variables behind. We do that same thing again. Now we have 2 variables in level 2e, and recall that any 2 variables in the same level can be contracted up at least 1 level. That gets us to level 2e plus 1, and by Hensel's lemma, we're done. Okay, so that's the first one. The second one, Suppose level K contains at least m plus 6 variables, and the level right after it contains at least one variable, and the form has a non-trivial 0. Okay, this one is a little more work to go through. So if any pair in level 0 can be contracted to level 2e, we go ahead and do that, and then we have m plus 4 variables left in level 0. Of course, this is enough to produce another one in level 2e, and we're done. So we assume that none of the variables go to level 2e. Now, if a pair contracts to level 1, so just one level up, there's already a variable there. We can perform a contraction, and we know by the previous reasoning that it's going to be free in all the even and odd levels up to 2e. So that'll zip straight up to 2e. We're left with m plus 4 variables in level 0. And again, we can produce another variable in level 2e, and we're done. So finally, we assume that none of the pairs in level 0 contract to either 2e or to 1, which means there are at most m minus 1 possible bins, possible odd levels for it to contract to. So we need at most, m plus 2 variables in order to get two pairs to go to the same odd numbered level. So we perform that contraction. It uses up at most 4. We're again left with m plus 2 variables. And just as before, that's enough to perform a contraction to get all the way to level 2e. We contract those two variables and we're done. Okay, it's all downhill from here. Suppose, let's say level 0 contains m plus 3 variables and level 1 contains at least 2 variables, and the form has a non-trivial 0. We'll use, by that first lemma, at most 4 variables from level 0 in order to produce a variable at level 2e. Because m is at least 3, that leaves at least 2 variables in level 0, and we assume that we have 2 in level 1. And so we perform that sort of overlapping contraction lemma to get another one in level 2e, and we're done. And finally, suppose level k contains at least 4 variables and level k plus 1 contains at least 4 variables. In this case, we just perform the overlapping contraction trick twice to get 2 variables in level 2e, and we perform another contraction, and we're done. And finally, let's put all this together. And I haven't been really doing a good job of keeping track of time. I was a little bit afraid that I wasn't going to have enough to talk about for the 40 minutes. But in our final piece of reasoning here, we'll take the number of variables that we assume that we have, divide by d, and that will give us the number of variables we can assume to be in level 0. And so because m is at least 3, we know that level 0 contains at least 4 variables. In fact, we know it contains more than that. And that the first 2 levels contain at least 2 times as many variables. And so it contains at least m plus 7 variables. And you'll note that that covers all the possible distributions of variables in the first 2 levels that were given to us by those four lemmas. Okay, that's actually the end of the proof that I wanted to present to you. Here are my references. You'll probably notice that I actually just screenshotted one of my papers and copied it in here because I don't know how to put references into a Beamer presentation. But thank you all for coming.